So I'm gonna do a totally different type of presentation here. These guys asked me to do more of a demo of the software, and I've always been told never demo software when you're giving a talk, because you know, if this is I'm being recorded, I got to watch what I say here. But certain software applications are GIS. I'd never try to do this, but this is a testament to how robust the software is. No pressure, no pressure, guys. I'm also going to switch gears completely in scale and scope. Go ahead and go to the next one. We had some legislation passed 10 years ago, and it instructed the USGS to go out and conduct some big, large carbon assessments, resource assessments. And what we're particularly interested in is this part of the carbon cycle, and that's the effect of major controlling processes on ecosystem carbon storage and fluxes, namely resulting from changes in land use and land cover, ecosystem disturbances, and potentially climate into the future. And so this is what I'm going to be talking about, but you know, I'm following on a bunch of highly detailed spatial thematic models with something you guys are going to look at and go, wow, that's coarse. It's preparation. Go ahead. The work here is particularly focused around the state of California and some work we got into to support the state's fourth climate change assessment. And what we did from a conceptual perspective is we developed a land use model, and we synced that up. We developed a number of projections which were passed to Leroy Westerling's fire modeling. He incorporated a bunch of different climate models and radiative forcing scenarios. He projected wildfire out into the future. And what we've done now is bring those back and then include a bunch of new effects, largely due to climate, on ecosystem carbon balance. Go ahead. The land use side of this was just published, I don't know, a few weeks ago in Earth's Future. So this would be a good reference, and we've got several other papers that we've done on our work in California, really around land use and how we've developed alternative projections, empirically derived projections. The STSM, so it's a very simple model compared to some of the ones you've seen, and as Colin mentioned, in fact, it really syncs up with the scale that was done in his work. But we've got these major cover types, land use types, and they, for the most part, correspond to what we can map relatively high accuracy using Landsat. The transitions are a fairly simple set, you know, changes in agriculture, so expansion and contraction, harvest, forest harvest, agricultural harvest, fire, urbanization, things like that. So again, we're zooming out here. Go ahead. You might have to click, there we go. Okay, and so one of the big things we worked on, we've been working on for a while, is development of the carbon stock flow model within the software. We call this LUCAS, the Land Use and Carbon Scenario Simulator. It's just what you guys have been working on, a STSM with stocks and flows. This is what our carbon model looks like. It's a very simple IPCC-based approach, single biomass pool, litter, a couple of deadwood pools, soil. We also have a leaching flux out to an aquatic pool. We have an atmospheric pool and some harvest products. Again, those stocks are in the model, and they're to preserve the mass balance, so we don't leak carbon, make up new carbon, something like that. And then these are all the flows that we've included in our simulation. Go ahead. I included this just to point out that we're doing quite a bit of work to modify that relatively general stock and flow model into something that looks more like this. This is based on the CBM CFS3, the Canadian Carbon Budget Model, where we have a greater number of pools, but I'd argue increased simplicity in something like this. And that's because we get the ability to always follow just one linkage instead of getting multiple things going into a pool and then trying to debug a model. So we're doing a lot of work building up this type of a framework. Okay, so the scenario projections that we considered, 4 projections of land use and land cover change. There's a business as usual, what we'll call a BAU, which is based entirely on about 25 years worth of pretty high resolution historical data collected by the state. And then we had 3 variants, a high, medium, and a low, which were geared around some population projections that the state had also produced. The difference in population between high and low is about 20 million people statewide by 2100. Considered 2 radiative forcing scenarios, RCP 4.5 and 8.5, probably familiar with those, and 4 climate models. And Brian, very much what Brian did, he showed the quadrants selecting the climate models. The state did that as well. So we've got kind of extremes and then a couple of middle ground climate models that were selected. And these are specific to California, those extremes. They may not match other places. And then we've also got fire projections run for each GCM and RCP, so 8 combinations, spatially explicit. I also calculated changes in radiative forcing, or the time independent, I froze on it. But anyways, this is the change in radiative forcing converted into CO2 equivalent, which maybe I'll have time or not, but I'll show you how I did it. And then we ran everything at 1 kilometer. And from a computational perspective, it was just 10 Monte Carlos of each, which is not all that satisfying. Go ahead. Okay, so how do we run them? We went to Amazon for this using EC2 to run all, what was it, 32, 320 when you multiply it times the iterations. We end up with about a 40-hour runtime. And we're running on this machine here. This is what it's called, and that's how much it costs per hour for a Windows machine. We ran 64 jobs at once, and the total RAM requirement was about 250 gigs. So a fairly modest computational lift is just the volume of scenarios that was driving our need to go somewhere like this. Go ahead. About 423,812. So this is just a little animated GIF showing what some of the land use projections look like. 10-year intervals, where there's the year. A couple of zoom ins around San Francisco Bay Area and the southern Central Valley showing growth of Bakersfield. You also see a lot of agricultural change going on here. Go to the next one. These are average annual transition probability maps, again, produced right out of the software. You can view these in the UI. We created some, what we did here is actually generate these over all of our scenarios. So they're not just created for one scenario, but averaged across all of them. Go ahead. And then this is just a single Monte Carlo randomly chosen from one of the runs. And it shows the changes in live biomass at what 10-year intervals down here. And anybody want to guess what the shotgun spray kind of looks like? Yeah, it's fire. That's the rim fire right there. You'll see it come in and then regrow. And then this is that plot I showed yesterday where we've taken all of these simulations, thrown them into R, and we calculated confidence intervals for our projections. But the message being ecosystem carbon storage in California is projected to decline. This is the historical period. This is the 2014 drought. We see the big decline immediately there and a kind of a continuation. But we do have some scenarios way out on the end, typically involving the cool wet climate model combined with the low land use scenario where you can get futures up here. The warm dry model producing really extreme declines in ecosystem carbon. Go ahead. So again, just to emphasize the scenarios, climate models across the top, land use here, and then our RCPs. And this is, again, just the net biome productivity between 2017 and 2100. Most of the models showing a decline. Really depends on climate model, which is emphasized in the next panel. Go ahead. This was interesting. I didn't expect this. I thought most of the variation in our results would come from RCPs. I thought the climate models would represent RCPs and produce pretty different results. That's not the case. The message that we're getting, if you look at the red lines here, is that the two RCPs for any one climate model really run together. The variation we're seeing is really due to choice of climate model. So that's a really important finding. If you're doing this kind of work where you're bringing in climate projections, you got 32 models to choose from, your choice of model, climate model, really makes a difference. Land use sits somewhere in between. It's important, certainly, but not as big as in your choice of climate model. Go ahead. Let's switch to the software. Time. Oh. Okay. So we'll just, first we'll just focus out here on the scenario manager. And so I just give you, this is how I did it. Some of you guys, you know, might look at this and come up with something else, but this is basically how I structure my my runs. I set up a calibration folder, and I do a series of calibrations. And when you're doing stocks and flows, you guys probably saw in the advanced class, model run times slow down. It can make a difference. And so there's also this whole carbon calibration issue and spin up that you really need to consider when doing carbon. And so I've developed some methods around both non-spatial and spatial calibration runs, but they're kind of single cell runs. And so the model, I can run it for 1,000 years on a single representative cell and help derive and debug the model. So that's what I've done here. I also use a single year spatial run. I won't get into all the details about it, but I use that to help develop carbon initial conditions, which can be a very challenging piece of work to kind of crank through. And then, so go ahead and just open up the, I keep everything organized in sub-scenarios. You'll see why. Go ahead and open up the final scenarios. Sorry, that's just the sample, what it looks like. But my final scenarios, I group into my different land use scenarios. And then if you just pop open, let's say the BAU, you'll see that I've got one climate model, RCP, per land use scenarios. This is the way I've organized it. There's 32 of these individual scenarios all set up, ready to go. Okay, so this happens to be the business as usual CAN-ESM model over here on the right. And I'm just gonna walk you through the screens. And it might be useful if you see something that needs a little more explanation, just let me know as we go. It could be easy to get lost, but I'd like to say that I fill out all this important information every time I run a model. But the reality is I did this yesterday when I was thinking about doing it. So I remember at one point I had to ask Leo, hey, there was actually a character limit on there that we had to open up at one point because my Hawaii model wasn't there anyways. I suggest using that. So run control, simple. We're running from 2001 to 2101. The reason why 2101 is because when I output raster stuff, I only go at 10-year intervals. And so I just do it like this. We run the model spatially for 10 iterations. Go ahead and do the pathways. We zoomed in, but basically it's the same pathway diagram for each of our strata. So our strata, in this case, I should have mentioned, are ecological regions. We have 12 that fall in California. They're based on EPA. And then we have counties, 58 counties. So that's how our landscape is stratified. And it's a very simple model. You can go ahead and right-click on forest and open that one up and just give you a real quick sense of what this looks like. We'll have a number of transitions, but again, all of our base probabilities get set to 1, and we're gonna go modify those in one of the other places that the software allows. The only thing that's a little bit unique is this proportion applied to our fire events. And so this corresponds to severity. And so we use historical fire severity to parameterize the model. And I should say this is a fixed variable, and perhaps one of the things we may want to explore with future sensitivity tests. What happens if we start changing the makeup of fire? Okay, we can go ahead and click over to initial conditions. Everything in this model is spatially explicit. So we're just loading in our rasters here. These were all prepared in R, but I admit I click that little button and do the file browser and go find it and load it in. I didn't use R to push all the stuff in. Yeah, all right, old school, man. All right, let's go to advanced. And I want to show you, this is something that was a game changer for us. So we use a lot of historical data in the model. We'll load historical distributions of data and then we sample from it. And the old way to build that projection would be to, in R something, create this monstrous area target file that could be, I've had some that are 5 million records long. Absolutely awful to deal with. And that was so that we could sample from historical data and preserve covariance. But as you guys, at least in the advanced class, saw that we can do that now with, I don't know, there's probably 1,000 records. And so what we do here is we load in, this happens to be the historical rate of urbanization in Alameda County. We've tied it to an external variable, and these represent years. And this is then our amount, okay? And so if we go to external variables, all I do is tell the model, for these historic years, let's just go ahead and grab the historic year. We want to simulate what happened that year. And then we get to a period where our historical data end, we run out of remote sensing data, and we want to go ahead and start our projection. And here we're saying select a uniform integer between these 2 years and go out and get it. And what happens in the model is all of our land use change transitions take the same sampling. We preserve covariance across sector or transition type and space and time. And then it's very simple. You want to create a new scenario, just change the years at which you're sampling. Focus in on a high urbanization period in this case. So much easier. I can't tell you what a game changer this really was. And then transition targets. So here we're just saying now for urbanization, go get that historic rate. We do that for some of these agricultural changes as well. But we've also got several other examples here. We have a transition target of 100 square kilometers to convert annual crops to perennial crops. What else do we have? We've got thinning, which is turned off here. And then we've got our fire data. And so this is the data we're pulling back from Leroy's fire simulations. And what we've done is for every ecological region, working with Dave back here, we summarized the distribution across what was 1,000 runs from Leroy's fire model. So we get a statistical distribution from which we sample now, coming from an external model. Okay, and I think back to advanced, I'm trying to remember my order. And then transition multipliers. And so we also use multipliers for a couple of things, and these represent parameters that we have lots of uncertainty in. One is in California, they often remove orchards, almond orchards, when they get to be a certain age, but there's a lot of uncertainty in that window of age. Could be 20 years, could be 50 years. And so we allow the model to sample. We've calculated a uniform min-max to represent the cumulative distribution of turning over 95% of your orchards when they reach 50 versus 20. And then we've also got this thing where we convert perennial crops back to annual, and it's got a time since transition. So we're pulling a bunch of levers here in the model to represent different types of transitions in different ways. Okay, what are we at? Transition spatial. Okay, so now the only thing we use transition size for is fire. And this is another big caveat in the model where we kept severity fixed. We're also keeping the fire size distribution fixed. This was calculated from the FRAP data set, California's fire database. And so that's held constant. We're not changing the size distribution at all in time. We do heavily use spatial multipliers. And so we've got, as Colin showed, very similar to what he did, we use things like the US PAD, the Protected Areas Database, the US, to help control some of our land use transitions. You know, we're not going to harvest wilderness area forests, simple things like that. But then what we've also done is bring back in that fire data. So part of Westerling's fire simulations were spatially explicit, but the cell size was 36 square kilometers, 6 by 6 kilometer resolution. And so we took those data, resampled, and bring those in as a relative multiplier. Remember, we're hitting the model with a target of fire area, and we're just using this now to help guide where, the pattern on the landscape, and we're trying to be as in sync with Westerling's projections as we can. Okay. We have adjacency. We use adjacency a lot, so when we grow cities, we want to grow cities around existing cities. We don't want to start a new Fresno in the middle of Lake Tahoe. So this is a great feature for just preserving that kind of fundamental geographic rule of kind of time distance decay, right? So we use this to control lots of our things without using spread. We're just saying lots of these neighbors are the same. Keep converting. I think Colin, you had it in one of your slides. Okay, state attributes. So when you guys did the carbon model, you heavily use state attributes to help initialize your model. You also used it to drive NPP. We do a lot of the same stuff, but there's a lot of other things we track. These are in here to control our adjacency, but I mentioned albedo. And so a colleague of mine in South Dakota did a big project where he calculated ecoregion albedo values based on land use and land cover classes. And so we've included those in here as a ecoregion state class value. I'll scroll down here, see if anything else jumps out. Here's another thing that I think is important in some of the bigger models that you'll be running. Tracking age within the database can take your models from 1 record to 20 if you tracked age every 10 years for 200 years. So Leo suggested we do it this way. It really cuts down database size. And then we've got some NPP projection down here. I think that's probably good for state attributes. Okay, and now into the really fun part, the stocks and flows. It's not too bad. Yeah, so this is again what that stock flow diagram looks like. It's a pretty straightforward carbon model. So nothing too fancy about this. Go ahead and click on the flows. It doesn't take, yeah, good. It's already loaded in. This just gives you a sense for what that data might look like. So for the coast range, ecoregion, forest, let's see, living biomass, converting to standing dead. So this would be like a mortality rate of this. Okay, so that's a time series of these flow rates built into the model. Go ahead and go to initial stocks. We've initialized all the stocks. Again, I had to do a little bit of calibration here, but they're all rasters that we've developed. So this is an important put options, or I think we can skip it, pretty basic. There's also several groups of carbon stocks or flows that you immediately want. One might be net biome productivity, which is your NPP minus your NEP minus any removals from land use or fire. So these are kind of things that you immediately look to. And so we calculate them here as a group. So they're ready to go. Go to the stock groups. Same thing here. We immediately want to know what's the total ecosystem carbon storage. So we just add up our ecosystem carbon pools. The model handles all this for us. We have flow order. You can spend some time right here, but we've developed a method to process all of our flows in a particular order that preserves all the correct parameters. And then flow multipliers. So this is where we really start bringing climate in, and I think is a really neat piece of what we've done. But for any ecoregion in any year, we modify several of our parameters in response to changes in climate that year. We have an empirical model of NPP that drives changes in growth. So here we can see what's that, about a 4% increase that year in that ecoregion in our NPP. But at the same time, we're also modifying the rate at which dead organic material decomposes due to changes in temperature. It's the Q10 function that's calculated. And so we're consistently using and match synced up with all the climate models, RCPs driving fire and all of these DOM pool responses. And then the last real big piece is the flow spatial multipliers. And so we had a decision to make. Do you make those temporal multipliers that I just showed you, the flow temporal multiplier spatial every year? That's a lot of rasters to deal with. The bigger thing is that almost all the time, climate data is much coarser in resolution. The LOCA data is about 6 kilometer by 6 kilometer. What we did is represent within strata variability in, say, NPP. The northern Sierra grows at a faster clip than the southern, and we create a growth multiplier which is static in time. So this is perhaps a limitation because the growth within a year isn't moving around within a system. The pattern is fairly constant. but that's just a generalization and a trade-off that we make for computation. So that's sort of the model. I don't know if there's time for a question. I can half a question.
No, a question or two.
Okay.
It's just me talking.
Oh yeah, we got all kinds of time.
So in the distribution, you randomly pick the year that corresponds to the historic time. Eventually, you end up in the future where you're using.
Yes, I'm sorry. Go ahead and close that.
So do you revert then to a time series that you import?
No, I'll show you. If you
can't pick a
let's
year.
get to the graphs actually.
If you're picking a year,
I think if you just so there's a bunch of them. So why don't you pick the transition? Yeah, here we just blow up our transition groups. You can get a sense, kind of, Louis, for what this does. So historically, we're matching the historical rate, exactly what we want from the historic data. And then once we get here, in this case, for this particular thing, we've picked a couple of years from our historical data that we want to sample from every year into the future. So here we're saying we want lots of agricultural expansion. And historically, the years that had that high rate were whatever they were. And so we reproduce those high years with some uncertainty into the future. You could sample from, I picked two scenarios where we're high land use and a low land use. That's why you see it like this. But in the business as usual, the range of values is like that. We're sampling from the full historical range.
I don't just I don't get
a common approach that we're using a lot, which is in the historic. We did it in the advanced course. So in the historic period, for a year, we use the historical record for that year.
Yeah, you pick randomly the year to match the.
Well, historic, we don't do any randomness. It's 2012. We use 2012, right? That's why you get the variability. Okay, might as well. We know exactly what's there. Once you go into the future. In our advanced course, we use the full historical record as the full range of possible variables.
So this thing.
And in any future year, we pick a year at random from history for that year of modifier. So what you're assuming is the past years are all independent of each other. You're sampling them as if they represent the distribution of what happened.
Yes, what I'm concerned about is the added effect of the climate scenario of
the GCM.
Well, telling you, it's not historic anymore. You're like
that's right.
Up here, so
we make the fundamental break in these scenarios that the GCM is not driving land use decisions. That land use decisions can operate independently, which they can. Yeah, not vegetation. You're right. That would be a problem if you were modeling vegetation. Yep.
I have a more basic question.
Okay.
So how long did this take you to put together?
I mean, this has been a work in progress for years, but some of this I was going to talk about a little bit later in the discussion. These pieces, the software tools that enable us to do this, some of them we've just gotten. Brian mentioned flow multipliers are here just recently. So I've been working in this field for 15 years, working on a land use model with these guys for 2010-ish, a little something. So I can't tell you that I sat down one day and said, oh, I'm going to build this model. It didn't work. It's been an organic thing. Parameterizing this thing is once you have it scripted in R, it's pretty quick. Now, it's pretty quick.
I think getting the data to parameterize.
So the external data that we depend on, we talked about this a little bit yesterday in the course. There's not a lot. There's climate data. So we've got a bunch of loca downscale climate that we needed to get. There's PRISM historical climate data that we needed. There's historical rates of land use change that came from a California county-based aerial interpretation project. So we've been pulling those together for some time. But again, that's an external piece that we're relying on. Fire data, not an overwhelming amount of historical data. I mean, certainly not by size or volume or anything like that. More work, I'd say that the biggest area we've spent time on is we rely on remote sensing a lot, and remote sensing is great at land cover, but this is mostly land use. And so we've had to figure out how to translate cover to use, and that's not a trivial exercise.
And then one more question, and then we'll wrap it. Okay, and maybe this is like a table for the discussion this afternoon as far as way forward.
Yeah.
This mention of remote sensing, and Louis mentioned it's the most expensive part that's sort of implicit in a couple of the talks. I don't think it's part of the software, so I'm curious about like how that integration works, and if there's anything in a sort of best practices, most affordable method type of, take advantage of whatever USGS or NASA is producing versus the new satellites that are coming online, like the planet data that's 1 meter, 5 meter.
We can probably expand on it in the next one. My initial reaction, because I spent a lot of time on this, is that it's the Wild West right now. The availability of Landsat has created people like Dave and other folks that are pushing boundaries, producing new things that someone like me is trying to figure out how to synthesize, and it's challenging right now. Great opportunities.